Hey, glad everybody can come to this after eating lunch. I'm glad you guys will fall asleep during my dry technical talk. So hopefully you're caffeinated enough to keep up. We got a lot of details to cover, so I'm going to kind of slide through a little bit what we're doing for the overview. So I'm going to be discussing a bit what exactly is secure computation, what technologies can be used for secure computation, things like MPC, Ts, trusted execution environments, and FHE, as well as the shortcomings of each of these approaches, and the solutions for the FHE-based approach and what Nucypher has actually accomplished recently and what we are working on. So we'll be very quickly and briefly discussing just the MPC and T stuff so I can spend more time on FHE. So that way if you have questions, we can actually get through those. So let's dive right in. What is secure computation? Typically there's a requirement for privacy. In this case, there's parties, usually somebody needs to perform a some function f on some inputs, in this case x and y, and in this case there's usually a requirement for that privacy where the data x or the data y may not want to be revealed when you're doing some sort of computation or the output of that, and the computing party may not want to reveal that. In this case, this is a two-party secure computation scenario that I show in this graphic, but it's not specific to this. It can be a single party or it can be multiple parties. So the requirements for zero knowledge in secure computation are not required, but they may be present. And typically in a secure computing environment, there is a lack of trust in the computational setting, whether that means like it's a network level adversary, a computational adversary, as in the person doing the computation, or if it's done on, or maybe you don't trust the hardware in case of like, you don't trust the hardware that the computation is actually being performed on. In either way, there is an adversary that exists in our situation that threatens the confidentiality and the integrity of that data. Solutions can exist in both in hardware and software. We'll be discussing which of those, and I only have one, which is like something like Intel SGX or trusted execution environments that are built in hardware. And we'll also be saying how that software security is achieved. And as well as for secure computation, the threat models for specific secure computing protocols vary greatly, and they change based on the solutions that you use. What may be considered secure in one setting may not be in another, and it depends very heavily on what your use case is. So, in some use cases, it's okay to leak some information. In some use cases, it's not okay to leak any information, right? So, to give a brief overview, talking about multi-party computation, it can be considered a software-based security protocol. The security reduces to a cryptographic primitive used. In many cases, people use Shamir secret sharing, and we can actually reduce some of the security to the mathematical properties involved. And in this case, what happens is we have multiple parties that will perform a computation, and the computing parties gain no knowledge of the inputs to a specific circuit, right? So the input data in the beginning is split and then shared across to all these computing parties. And at the end, it's then reconstructed at the end by somebody. And at this point in time right here, this is the only point in time when any data is actually leaked. So in that case, we're not leaking any data during the circuit computation, but whoever reconstructs the output of that circuit will actually learn some data. In a trusted execution environment situation, there exists hardware. It's a hardware-based security protocol, which essentially means that the security reduces to the safe implementation of an enclave or a specific dedicated part of a processor. It literally exists as just a separate secure, in quotes, secure partition in silicon. Most implementations of Ts are vendor-specific. I give some examples here, which are like something like Intel SGX, AMD PSP, and ARM Trust Zone. It requires a client API to communicate with the enclave. So if you can see in our diagram here, we have a client API which will communicate with the processor itself and allow the application to be executed inside this enclave, inside this secure part of the processor. There's problems with this, and we go over those as well. But essentially, we're going to have an operating system that runs directly on the processor itself for that execution environment, and then it will perform whatever API call you tell it to perform. In this case, they can be function specific, so it doesn't have to be some generic, it can execute anything, but there's things like hardware security modules, which are also forms of trusted execution environments that may do things such as key generation and signing or encryption dedicated to a spot. And these are in wide use today, but some other things like SGX may not be in more wide use than, say, a TPM or HSM, like I said. So now we can get into the meat of what I'm going to be discussing here. Fully homomorphic encryption. So it is a software, you could say software-based security protocol. We can reduce the security to hard lattice-based cryptographic problems. The most practical implementations reduce to learning with errors, which is actually a quantum-resistant problem. So if there exists a really strong quantum computer, this is incapable of being broken by that quantum computer. So FHE solutions exist for both single and multiple parties, which means like we can have a single person. When we have this in our diagram here, we can perform a function, so like a circuit evaluation here. We can have a single party perform that function, or we can have multiple parties perform that function, and in which case that would be something called multi-key FHE. So in this case, in fully homomorphic encryption, the function is computed directly on our ciphertext. It's not computed on the plain text. So we can actually encrypt some data, and if we look at our diagram here, we can take some plain text M, pass it through an encrypting function, and get the encryption of that. So we have a ciphertext here. We can evaluate any arbitrary function f on this, and the output is the function computed on the plain text itself. It would be the exact same output had you performed the function on the plain text there. So it's, in short, it's the equivalent of performing the computation on the plain text, just encrypted. What we can refer to this as is, and frequently when we talk about homomorphic encryption, we say things like the plain text domain or the homomorphic domain. What that means is, when we say we compute something in the homomorphic domain, it means we compute some function, some circuit or function while the data is encrypted. So the data that we're computing it on is encrypted. So that's how that works. There's two keys that are used, typically, and depends on the scheme that you use, but in the schemes that we have worked with, we have two keys. And we have an encryption key, which you're familiar with symmetric encryption or public key cryptography. We can encrypt some data and then decrypt some data. And our computation key enables the computation on that encrypted data. So to actually perform this evaluation function here, homomorphically, it requires that you know the computation key here, okay? So briefly going over some pros and cons of multi-party computation. Circuit designs with MPC are relatively straightforward. They can be constructed with Boolean logic gates. Debugging is also straightforward as well. And it's very clear. You can just perform a reconstruction at any moment in time whenever you're in the middle of your circuit. Say you're designing your circuit and you don't know why you have some value. Well, you can just reconstruct what you have at that moment in time and see what it is and do it. I notice I'm not saying it's easy, but it is straightforward. You can just pretty much say, give me this value, and reconstruct it and do whatever, and you can get that information. The proofs reduce to relatively simple secret sharing schemes. The proofs for those are, I say, relatively simple. Mathematically, they make more sense than, say, something very complex, But some cons of this. Many constructions require additional zero-knowledge proofs for security. So, for example, threshold ECDSA, which has recently amassed some really cool following, and I do think it is very cool, but it is kind of difficult because you actually have to include some relatively simple zero-knowledge proofs to ensure that the protocol is secure itself. So the protocol does not just include Boolean logic gates. It also requires zero-knowledge proofs in there. Branching is also either impossible or makes it really complex to perform. So when you perform some MPC operation, it's going to require a ton of complexity just to be able to perform some branch, if you can perform that branch at all. And security-wise, operations are still performed on plain text data, although split. Depending on what your threat model is, if there's a collusion adversary, this may not be preferable to you. So if that's the case, this may be sort of a not so great thing to use. Now, the biggest problems with MPC come with scalability. Complexity grows linearly with the circuit at best. That also you also then have to include zero-knowledge proofs, which can add quite a lot of interactivity between the parties involved. And network overhead is very, very large. Depending on some schemes, may require exponential communication. So if you have 3 parties, it would require like 3 to the 3 communications back and forth. There's a huge liveness requirement. An offline node can block the entire protocol from continuing, so you'll have to wait for that one party to come back online to perform something, which isn't great. And any network latency can have absolutely horrible effects on these protocols. It will pretty much cause, if you have to wait 10,000 milliseconds to communicate with one party, well, since it's exponential, you have to talk to them many times. It's a few thousand milliseconds that you have to continuously wait to finish the protocol. So now moving on to trusted execution environments. Circuit design is also relatively straightforward. It's not necessarily like a circuit like you're used to hearing with zkSnarks. But it uses a very similar API to what you'd normally just be developing with any other library like OpenSSL. It's easier for your regular developer to look at and reason about and build on. Scalability, computation only requires the liveness of the computing party, really. So you can encrypt some data, send it to the computer that you want to compute on, and it can perform some computation inside this environment. There is also some network latency there, but we'll dump into that soon. Debugging is quite complex on SGX, or really any enclave, unless they build a specific interface for this, which arguably might make it more insecure than it already is. There is no way to really just peek into an enclave and see what's going on. You have to provide a ton of print statements and just really see what's going to happen in the enclave and then pull it out and see what's going on there. There's no way for you to look inside the enclave and see what's happening in comparison to something like a software-based protocol where we can, just reconstruct it, like I said, with MPC and just see where we are in the current state. That's just not possible with SGX. So you have to print a lot of data, provide a lot of debug statements, and just try to figure out where a problem is. It would probably be easier to construct it outside of SGX and then move it on the inside, but sometimes that's not possible. Security. The reductions, if you can call them that, are basically the difficulty to exploit hardware, which, as we've seen in the case of Spectre, Meltdown, especially Foreshadow, these just aren't that secure. As much as everybody wants them to be secure, we wish they could be secure. Unfortunately, they just aren't that secure. The attack surface for modern processors is absolutely massive. And if you talk to researchers in this space, while we are confident that eventually someday we might find something and build something that can withstand a lot of attacks and scrutiny, there will inevitably be a break in it. And that's just my opinion as well, but also I think the opinions of many researchers working in this space. For example, Foreshadow, which essentially allowed the researchers to attest to any computation for the keys that they leaked from SGX. That was a massive break. Another problem is that it doesn't really work well with trustless technologies. You obviously have to require trust in the vendor that Intel not only is manufacturing it correctly, that they're not hiding backdoors in this as well. And given what we know about the Intel management engine, this also seems like a kind of bad assumption. We can't trust that vendors are going to do the correct thing all the time. There is no working open source implementations as of yet. Intel has worked a little bit to open source some of their technology, but it's still, none of it is really open source in the true meaning of the word. And any hardware updates still require actual hardware replacement. I can't just update my CPU easily, nor can you get your stakers or miners or whoever to update their CPUs easily. It's more easy on, say, you can still deprecate some old process, but that means you have to get everybody to spend, upwards of maybe $1,000 to a few more $1,000 just to upgrade their CPU to fix a security vulnerability. Not to mention, there is no way of knowing if anybody actually exploited their machine. That would require some weird oracle that I also don't think is possible. So now we get to jump into FHE. Circuit design is also very, very easy to do in this case. Things can be constructed with Boolean logic gates. The talks before, Isaac and Harry gave great introductions to circuit design there. And this, if you're starting to reason about how to build logic gates and circuits in snarks, you can probably easily figure out how to do this as well in FHE. As Isaac put it, the snarks don't necessarily have bit stuff. So you have to use actual mathematical operations to perform this as well. But FHE actually provides a nice interface into using bit stuff. So if you like bit stuff, then you'd like FHE. But there also exist schemes that don't also necessarily require binary logic gates. You can also use integer operations, and we'll be talking about approximate arithmetic here in a second, which there are schemes for that as well. Security, the operations are performed directly on the ciphertext, and it requires a computation key to perform the operations itself. So this can actually add a lot of great value to a protocol where you can grant access to who should actually be able to compute. It's not just anybody, it's who you designate access to, but this also has downsides. We'll talk about that here in a moment. For scalability, like I said, it can be performed with a single party or multiple parties with multi-key FHE. And it only requires the liveness of the computing parties, right? So you can send some data to that person and they can compute it and send it back. But beyond just sending the data, there isn't necessarily any interaction required between the two to perform something. However, branching is also impossible, or it requires really complex protocols at the current moment. So I'll show a diagram here in a moment about that. So I'll leave that little discussion here for a little bit later. A big problem with FHE at the moment is that since homomorphic encryption is inherently malleable, the best security achievable is CPA, chosen plain text attack security. Typically what you'd want is CCA security for anything in the real world. But the highest we can achieve is CPA security. I'll get a little bit more into that a bit later. But bootstrapping, what bootstrapping is, just to give a very brief overview on it, it gets really technical really fast. But to actually perform this computation, like I was saying, it requires the computation key. That computation key is an encoding of the actual encryption key. So when you perform a fully homomorphic encrypted operation, what happens is you use a bootstrapping key that would be called that's also called the computation key. But essentially, as you perform operations on ciphertext, what you call noise, like you have to imagine, like if we're speaking about radios or radio signal, as you go into a tunnel, you may lose signal and it becomes more noisy and you hear more white noise. Very similar things happen to homomorphic ciphertext. As you perform computations, noise grows on the ciphertext, and the more operations you perform, the less you're able to do to the ciphertext. Eventually, it hits a ceiling or a threshold where no more operations can be performed, and the decryption is not possible anymore. What bootstrapping allows you to do, this was created by Craig Gentry in his seminal thesis in 2009, which gave us the first practical, or not practical, but theoretical FHE implementation. Essentially, it encodes the private key of this FHE scheme and then allows you to homomorphically perform a decryption. And this gets really complicated and why I'm not diving into it a lot, but it performs a homomorphic decryption while the data is still encrypted. and then it re-encrypts it. So that way it reduces all the noise and refreshes the ciphertext and gives us a nice new ciphertext that we can perform any operations on. That's why we can perform any arbitrary function on that. So the following, when you encrypt or when you encode that private key, like you can literally think of a computation key as a homomorphically encrypted private key of that encryption key, right? So that's called circular security. Matt Green has a fantastic blog post about this. I have a link in the presentation on an upcoming slide. But if you want to learn more about what circular security is, you can go on Matt Green's blog, and he has just a fantastic write-up about it. Another problem is ciphertexts are extremely large. 16,000 times expansion factor in TFHE. That's what we implemented in Nucypher's NewFHE. Computation keys can also be large, around 100 megabytes in TFHE as well. And performance speeds are kind of slow, depending on computation environment. However, we're going to be discussing all these cons in the next little bit here and say what solutions we have to this. So not all hope is lost. Not everything is bad and broken. There exists great research on how to actually solve this and what we can do to actually make it usable right now. So we'll go into circuit design. Like I said, branching would require pre-computed values or interactivity between parties. This kind of logic, if true, do this, if false, do this, absolutely not possible. To do that, it would break chosen plaintext attack security. Like clearly, if you have some sort of logic that says, if this variable is this, then do that. Of course you can't do that on encrypted data, right? It's encrypted, you don't know what the data is. However, compilers are also being used to create easier built circuits. Okay, so very similar to what you would have with like Snarky.js or other implementations for snarks. We have compilers that are being developed to actually make it so easier to build this stuff. In fact, one of our hackathon winners at ETH Denver, they were called Trustless Health. They implemented a WASM interpreter to FHE logic gates, which was exceptionally cool. So you could write your logic gate, your logic in Rust, compile it to WASM, and then interpret the WASM to perform the homomorphic operation. Very cool stuff. Chris Pikert also has great research on his paper called Alchemy. It's more of an academic project. It's called a language and compiler for FHE made easy. I have a link to that there as well, and also a link to our hackathon winner there. Various schemes exist for different uses. So if you want a different type of circuit that is different from, say, binary logic gates, then you can also use something like Heian, which is great for machine learning. It uses approximate arithmetic, which I'll basically just describe as like, say, you don't need an exact answer to some mathematical operation. You just need something near it, approximate to it, so that you can, perform some operation like machine learning or neural networking, right? TFHE uses binary operations. And say you want to do both, but you don't want to use different schemes. Well, fantastic. There's a framework for this called Chimera that is currently kind of out there and getting some notoriety right now that we're also looking at. It allows you to have interoperability between Heian and TFHE. So meaning you can go between the different schemes and perform computations in either. So we'll get more into the security now. FHE is inherently malleable. Anyone with a computation key can perform any operation on the data, right? So only the encryption key holder can decrypt. But so since we have chosen plaintext attack security as the highest achievable form of security here, there exists also leveled FHE, which enables us to actually achieve CCA security, which may be more preferable, right? So essentially what it does is it limits circuit depth and prevents some arbitrary computations, but you're essentially saying, I will only ever do this circuit of this depth, but no more computations other than that. And we can actually form CCA secure protocols and schemes from that. And also, zero-knowledge proofs can be used to prove correctness in the computation to prevent malleability. So we can, theoretically, we may be able to say, are you sure that you performed this one circuit, right? So the example I always give is, say you want to perform a computation on 2 encrypted numbers, and you want to add them together. Say 2 plus 2. We may get the output of 4, and that's what you expect. However, because you can perform any computation, you can do 2 plus 2 minus 1 plus 1. And it simply gives you the same answer. But did you ask for that? No, you just want 2 plus 2, right? So we may be able to use zero-knowledge proofs to prove that the computation was the correct one. And that's something we are actively researching. And we need to learn more about that and see exactly how that can be utilized. But we are working very hard on that. Bootstrapping requires the weak circular security assumption. Leveled FHE does not, if you do that. I have Matt Green's blog on that, so if you'd like to see that, definitely check that out there. Leveled FHE actually doesn't require bootstrapping at all, since you can build a circuit that will work for, or build a scheme that will only work for this one circuit. You can do that. And then you don't actually need the bootstrapping part, but ciphertext size may vary, and we're getting into weird realms there. Ciphertexts are extremely large. So as you can see here, 1 megabyte plaintext is approximately 16 gigabytes of ciphertext. That sucks. But all hope is not lost. Ciphertext compression also exists. I have some examples of a poor graph that I pulled off of a nearly dead PDF. It looks like there. But essentially what we can do is before we perform a homomorphic evaluation on that data, we can actually encrypt the data using a generic stream cipher. Like, you're probably familiar with this as cha-cha-20, right? But we wouldn't use that. But we could use an FHE efficient stream cipher to encrypt the data symmetrically before placing it in the homomorphic domain and doing computations on it. What that means is we can encrypt the data before, as in the plaintext domain. Then, as it goes into the homomorphic domain, it gets encrypted, say with like a public key, and then gets evaluated using a just homomorphic decryption. So you do the homomorphic decryption on the stream cipher encrypted data, which will roughly keep it the same size as the original plaintext data. So it allows you to keep the ciphertext small in storage, but expand it in memory, which is great depending on what you need to do. Heian potentially only has a 40x expansion, which would be much, much, much better. But that's kind of research level right now. We're still evaluating that. And also Heian, the authors, we're still trying to figure out how that may be used. Performance speeds can be improved from GPUs, ASICs, and FPGAs. NewFHE has increased performance by 100 times in the GPU. So you see TFHE normally has 13 milliseconds per bit. We actually achieved that speed up to 0.13 milliseconds per bit, making us, as far as I know, the fastest fully homomorphic encryption library available. So that's pretty cool. And on the GPU, we also have NTT, so that's with FFT. We can also use NTT, and still roughly 0.35 milliseconds, same speed as CUFHE, which is another FHE library. But of course, this can also be improved with GPUs, ASICs, and FPGAs, which is something we're interested in. So that's the talk. Obviously, a ton of extra information, so if you have any other questions, ask them. Please see me after. I may even do a breakout session if anybody's interested in talking more about this and explaining some of these concepts. But feel free to go on our website, nucypher.com, join our Discord, email me, tweet us, and definitely look at NewFHE. Thank you.
We have time for a few questions if there's anything anyone wants to ask right now. Otherwise, we can take it to the breakout session afterwards, maybe.
Hello. So I have a question on the decompression. So this means that have you implemented this Trivium cipher in the hybrid homomorphic way?
Your question is if we have actually implemented it yet? No. This is all, if you read a lot of the FHE papers, they explain how to actually achieve this compression. But it's not, I'd say it's outside of the realm of theory, in my opinion, that what we need more so is the existence of an FHE efficient stream cipher and to prove the security of those ciphers. There's some examples here in this paper, and I have that link there if you'd like to look into that. But essentially, you just need to implement that. It's relatively straightforward bringing that out of the papers and into the practical applied realm, but it seems pretty straightforward, right? You just encrypt the data and then pass it along into the FHE cipher, and then it can then perform like a decryption circuit in the homomorphic domain, perform the computation, and then you're done. It just expands into memory. Make sense?
Where we also try to implement AES as homomorphic circuit, but it takes a really long time.
Right. AES does take a long time, but that's also because it's not an FHE efficient stream cipher. So there's been research into finding something that is much more efficient than AES, right? As far as I know, actually, we have sped up AES computation in FHE actually quite a bit now, but it's still, not that practical. We'd much prefer something like Crevium 13 or something.
All right. Thank you very much.
Thank you.